All right. Well, the recorder is on, and it is 6 o'clock, so I'm going to get started. And it's on the wrong screen right now. Let me switch it back to the proper screen. All right. Go. All right. So a few things. I finished grading the homework that was due this Monday. And quite a few people did not follow all the steps. Okay, I didn't take off too many points this time, but next time I'm not going to grade anything that is not turning in the way that is not worked on the way it's supposed to. So some people did not use the original file; they just start off a new LibreOffice file and copy and paste something into it. Okay, so you got to start with the file. You got to start with downloading the file from the assignment itself. Okay, and then you work on that one. Some people forgot to put a name into LibreOffice. So when I open the file and I look at, okay, who's the author of this particular file, it was blank. Some people used Excel to edit the document, and I was able to tell because it left behind a little trace that I was able to find. So that is not what it is supposed to be either. And let me see, what else? There was one that was kind of like complete copy and paste. So it was copied and pasted from another source, another document. Yep.
I renamed mine.
Huh?
It had like trace nested was the name of the homework, and I put my first name in front of it. I didn't know if we were supposed to do that or not.
Say that one more time.
So like the file name itself
Mm-hmm.
is trace nested,
Mm-hmm.
and so when I submitted it, instead of having it just say trace nested, I put my first name.
It's not about the file name itself. It is about LibreOffice. So if you have to go to LibreOffice, go to Tools, and then go down to Customize. Nope, Options, sorry. Go down to Options. So go to Tools, and then go to Options,
Oh yeah.
and then the user data has to be reflecting your name. So that's what I'm referring to.
I did the same thing, but you gave me four.
Okay. So if you have any questions about why you did not get certain points, just send me an email.
Yeah, you mentioned about this file, but
Mm-hmm.
I did the same thing.
You did the same thing?
Yes.
So the question now is, did you?
Up today for you and show you.
Okay. So it might be an order of operation because if you have already opened the document and then come here to change it, that may not change this part of the document. Because what I do is when I check your homework, I go to File and then I go to Properties and see if your name is reflected here as modified.
My name is over there, right?
Huh. That is interesting. I can check again, because I just.
My laptop, maybe I have
Okay.
other mistake.
Okay. So that's fine. And then the other thing I check is I go to Edit and then I go to Track Changes. So if Record Changes is turned off entirely, I know the document it was not opened or edited the way it's supposed to. So I check a few things and minor points deducted this time, but next time, please follow all the steps. If you're not sure about what the steps are supposed to be, let me know and I will help you figure that out. So are we good so far? So again, only 1 point out of 5, is allocated to whether the file was worked on correctly. The rest is about whether the logic is followed correctly and whether the convention is followed correctly. So I broke up the 5 points into much smaller points, and I don't think anyone got any really super duper deduction, except for the few people who did not turn in anything. All right. So any other questions about this class? No questions. All right. All right, so just a little bit of interesting stuff. Let me see if I can get to the share folder here. Nope, I don't have a share folder yet. So let me go ahead and create a share folder link. It's already here. It's just that I have not put that link into Canvas yet. And here's the shared folder. And let me get the link to it. And then I'll put it under course information. So under course information, I am going to include an external URL of that particular folder. And this is a shared folder for cisp300. Nothing in this folder is secret. If I accidentally put something that is supposed to be secret into this folder, it will no longer be secret. It will then be declassified. Okay, and let me make sure that you guys can see it. So when you click on this one, you should be able to see it now. And it will show something like this. This is the exam one from 2 years ago. So I lied. The last time I taught this class was about 2.5 years ago, not 6 years ago. So it wasn't quite as bad as I imagined. Okay. This is one of the things that we'll go over today is a practice test, because we are overdue. We are actually overdue for the first exam, because the first exam is supposed to be about 1/3 through the semester, but because this is an 8-week class, we don't have a whole bunch of weeks before the first exam. So that's why our first exam is going to be November 7th, next Wednesday. So I scheduled it on next Wednesday, so that you have 1 weekend to study, and then 1 class on Monday to ask questions. So this way you can study over the weekend, find out what concept you're not clear about, bring those questions on Monday. I will try my best to answer those questions, and then on Wednesday, we'll take the exam. The exam is going to be only 1 hour long, so we're not going to take up the entire class period for the exam. So do you guys want to take the exam first, or do you want to take the exam in the second hour? It's up to you. Okay, how many people want first? And how many people want second? Okay, I'm sorry, the second is the minority in this case. I don't, yeah.
If we were to do it second, would we be going over new material first, or?
Yes. So if it is going to be the second hour, then we'll talk about new material in the first hour, which may not work out that well, because that way you study, you cram all that stuff into your mind, and then you get that some of that stuff got thrown out because of new material, and then you take the exam. So that may not be the best arrangement. So I think first hour makes more sense. Okay. So we'll do it in the first hour, which means it's going to be from 6 to 7 o'clock. It is open book and open notes. You can bring anything that is on a piece of paper. No electronics during the exam. So if you have been taking notes using a computer or a tablet, you have to print out all that stuff to bring with you, because I cannot have people having access to a laptop or tablets or cell phones. So if you have those devices, you just have to put it into your backpack or whatever bag you have. Make sure that you do not access those devices during the test. But other than that, it is any printed or handwritten material you can bring, and there's no limitation on quantity either. Is that okay? Yep.
Do you know, have you already made the test?
Nope. But what I'll do today is to show you a practice exam, which is the actual exam 2.5 years ago, so that you can actually see the type of question and usually how I ask questions. But since I have not really made up the questions for this class, there's no guarantee that they will be, they'll be exactly the same or how similar they're going to be. Question?
Can you tell us what topics are going to be covered in the test?
Say again?
What topics are going to be covered in the test?
I am only going to go over topics, not excluding pre and post conditions. So pre and post conditions will not be a part of this test. Okay? It doesn't mean that it's not going to be on the next test. Okay? Just because it is not on this test, means it's going to be on the next test. So, but I'm not going to put pre and post conditions into this test. The material in top-down design will be included. But it would just be kind of like the operators. Do you know the operators, like mod? Okay. Do you know what a prime number is? Okay. Do you know if n mod f is 0, n is a multiple of f, that sort of thing. Okay. So are there any other questions about the scope of exam 1? No questions. All right. So if there are no questions, we'll finish up something that we kind of started last time, but not quite finished yet, and also the ungraded assignment, from last week because I kind of pushed it out a little bit late, so I didn't want to talk about it in the previous class. But today's class would be a good time to talk about it. So that's in the announcements. The last one of the announcements is an ungraded assignment. So the ungraded assignment is once again on pre and post conditions. This is not going to be in exam 1. Okay, the nice thing about recording my lecture is if I do put this stuff into the exam 1, you can quote my video and go like, but you said that it's not going to be in the test. I go like, don't. Okay, then I have to give you guys either not count that question at all or do something to compensate for that. All right, so with this one, the code is if x is less than 0, then x gets the negation of x, and if. And the precondition one of line 1 is x equals to k. I want you to get me what is the post condition of line 3. All right, so we'll go ahead and figure out what this code is going to do. And let's see, I'm going to use one of the mouse pads here. Yeah, this one looks good. Okay. Just erase the content and work on this. Okay, so pre-1 is already given, and it is just saying that x equals to k. So this is a technique to find out how the end value of x relates to x. Okay, so that's the whole purpose of the constant k here. K you can see as a variable, you can see it as a constant. It doesn't really matter because there's no code within this pseudocode that changes k. So it doesn't really go anywhere. All right. So this one is actually the same thing as a conditional statement, except the else branch has nothing to do. So if you want to see it this way, you can kind of look at it as this. So you can you can look at it as line 1. If x is less than 0, then line 2, same as the one that we have here, x gets the negation of x. Line 3, instead of and if, you can kind of say that this is else. So I'm going to use line 2.1 here to say, okay, I need to reline up everything now. Okay, there we go. Okay, so now we have line 2.2, which is doing nothing. So if you prefer, we can just say, do nothing. Okay, 2.3, nope, this can be line 3 now. It is just and if. Okay, so these two pieces of code are functionally the same. The one that is actually in the question is a simplified version because it doesn't say anything about the else branch. The one that I have just spelled out in mousepad is functionally the same, except it looks a little bit clumsy because I do specify the else branch of doing nothing. So do we have any questions about the equivalency between the shorter version that doesn't have an else and the longer and clumsier version that has an else? Okay, no questions about that? All right. So now we can continue with our analysis. Okay, so now we want to ask, what is the precondition of line 2? Line 2, by the way, is common to both of them. So the precondition of line 2 is the precondition of line 1 and whatever the condition is. Does that make sense? Yep, okay. So that's pretty easy. We just have to expand what pre-1 is. X equals to k, and x is less than 0. Okay, that's it. That's pre-2. So now we have to figure out what is post-2. Now, to figure out what post-2 is, you don't even need to know what to do with a conditional statement because line 2 by itself is an assignment statement. So what you need to do is to think about, okay, what do we do to an assignment statement when we know the precondition? How do we figure out the post condition? Only based on line 2. So now you look at line 2, you go like, if I look at the right-hand side of the assignment of line 2 as a function, so f of x equals to the negation of x, does that function have an inverse? If so, what does it look like? What do you think? So let me write it down here so it is all going to be recorded. So if f of x is the negation of x, what do you think is the inverse of x? I'm using f prime as the inverse. What do you think it's going to be? The negation of x. It has to be the negation. So the function is its own inverse in this case. Well, can we prove that? Well, let's try that. So the f prime of the f of x is f prime of the negation of x, which is now the negation of the negation of x, which is x. So that's why the function is its own negation. Okay, but the key is it does exist. So because the inverse function exists, which rule should I use? Should I forget or should I substitute? We should substitute. Very good. Good job. So we substitute whatever is in pre-2. Whenever we see the variable x, we'll replace it with the inverse function of f applied to x. So this is the first line. I always start with this, and then I just expand it. So what is pre-2? Well, pre-2 is x equals k, and x is less than 0. Okay. We find all the occurrences of x, and then we replace every occurrence of x with the negation of x. So now we can actually carry out the substitution. So now we just say the negation of x is k, and the negation of x is less than 0. You don't have to simplify anything. You just mechanically apply the substitution. That's fine. So that's post 2. And then we go like, how do we figure out what is post 3? Well, if we want to figure out post 3, we know that post 2 is one possibility. But then there's another possibility. The other possibility is, what if the condition is false? What if x is less than 0 as a condition is false? Then we have nothing to do. So that condition goes all the way, goes straight to the end, so it becomes a part of post 3 as well. Okay? So that means without using the longer version of this code and only using the shorter version of this code, we'll just say that, or the other way is the condition is false. Okay, it is not the case that x is less than 0. And there's one more thing that is true. Pre-1 is still true. In other words, x equals k is still true in that case. Is that okay? Because the alternative, which means when the condition is false, I do not do anything to x. If x is not changed, okay, if no variable is changed, then pre-1, which is really just x equals to k, is still true. But the fact that I went through the else branch means x is less than 0 has to be false. So those two need to be ANDed because they're both true. But it is only the other branch, so that's why it is ORed with post 2. So now when you expand the entire thing, because we also know what post 2 is, so now we have the negation of x equals to k, and the negation of x is less than 0. And that, let's see, I need an overall pair of parentheses here. And then you have the OR of the other side. So the other side, you can always look at it as x is greater than or equal to 0, and x equals to k. So if you get to this answer, I will consider it 100% correct. It looks really ugly, okay? Because the other thing we can also say is x equals to the negation of k, and x is greater than 0 over here. Or you can also say that k itself is less than 0. So there's a whole bunch of other ways you can say it, but mechanically speaking, this is where we can get to without much algebra. Is that making any sense? Yep.
So, like, if we were to get this question on this, would it have to be written this way for full credit? Because I got that answer, but it's written differently.
How differently?
Huh?
How differently?
It's just like I said, for like post 3, I said x is greater than 0 and x equals negative k, or x is greater or equal to 0 and x equals k.
That'll work.
It would work like that? But I mean, like, do we have to do like sub and...
Yes. In exam 2, in order to get full credit, you have to explain step by step how you got there. So using the sub rule is basically the mechanical way so that we can derive a post condition from an assignment statement. So you will need that when you answer a question in an exam.
Okay.
Because the exam is not just asking you what is the final solution, it is actually asking you, how do you derive the answer? How do you apply the tools that we have learned in this class to get to the answer? Okay, so that's a good question. Any other questions about this? It's all good so far? All right. So if this is all good, then we'll go to the share folder and we'll open up, the exam one from 2.5 years ago. So we'll take a quick look at it. By the way, you guys can open the document at the same time too. I have, in many of my other classes, students bring their own devices, and typically I would see a few icons up here because other people would also open it at the same time. The nice thing of having your own version is kind of two-folded. One is you don't have to look at the small screen in this classroom, and then the second thing is when I'm scrolling off to look at one particular question, you can scroll back to look at an earlier portion or a later portion. So you have a lot more control, over the presentation of the material when you use your own device to look at the same document. So that's kind of a nice thing if you want to do it that way. Yep, so we got an anonymous unicorn now. So I wonder when a leprechaun is going to appear. All right, so the rules are going to be about the same, but I'm going to go over that anyway, so this way you won't be surprised on the day of the exam. Because the worst thing you can do is to assume that you can do certain things, but it is not actually allowed in the exam. Okay, so the rule number, obviously, the time is going to be changed. It is open book and open notes, but no electronics. If you feel that you want to use a calculator, that's fine. Okay, you can use either scientific calculator or a very simple calculator, just no calculator app on the phone. Okay. This is an individual assessment, which means the score is intended to reflect the competency of the student with the name and student ID as indicated above, which is on the top part of that sheet, without any prior knowledge of the exam questions. Okay. It's difficult to get prior knowledge of the exam questions because I tend to cut it pretty close to print out the exam. So I don't think anyone can actually get a hold of that, because even I cannot get a hold of it. Answers should be independently and originally derived in the allotted time, observing all the rules applicable. What that means is, if someone said, well, I only got a little bit more to write, well, the time is already 7 o'clock, technically speaking, if anyone writes, after the time that I announce, like, this is the end of the exam, you have to stop, technically, I can just discount all of those people who are still writing after that moment. But I will give you guys a warning. I will give you like a 5-10 minute warning so that you know that, okay, it's almost, time is almost up. I better either hurry or I just kind of go like, okay, I'll just kind of go back and review some of the questions already answered. No sharing of open book and notes at material during the exam. So in other words, if someone just says, oops, I forgot to bring the trail map of a while loop, okay? And then that person cannot ask anybody else in class to share notes or printouts during the exam. Is that okay? Does everybody know what I'm talking about? Okay, all right. Do not discuss the question with any student who may not have taken the exam. Okay, so you took the exam, you walk out, and then the next day you meet one of the students on campus, and then the student go like, so what kind of question was in last night's exam? You go like, aren't you in the exam? Why would you ask me that question? So do not tell the student about the content of the questions, okay? You can use additional sheets of paper if necessary, because most of the questions are trace type questions, so you will use a lot of space. I will try to provide some space for you for all the answers, but sometimes some people work on something and they go like, oh, this is completely wrong. So instead of erasing half a page of material, they just kind of cross out the whole thing and then put the answer onto a separate sheet of paper. That's perfectly fine. You just have to make it very clear to me that, okay, this is not the answer. The actual answer is on the separate sheet of paper, okay? But you are responsible to bring the extra sheet of paper or extra sheets of paper, and also make sure you write your name on those paper, because otherwise, if I drop it or misplace it, I wouldn't know whose extra sheet of paper it is. Write legibly. I cannot give points to answers that I cannot interpret without post-exam explanation. So if someone just give me some squiggly as an answer. And then later on, after the exam, after I graded everything, come back to me and go like, but Tech, I really mean this is, x gets, x plus 5. I have no idea. I still cannot see it as x gets x plus 5. So I cannot, regrade or give points based on explanations of what squigglies mean. Is that making any sense? Okay. And then this question, all the questions have equal weight. I intend to keep that, which makes it easier for you guys to prioritize which questions to answer. Because if I have different type of questions and they all have different weights, then you have to look at the difficulty level of a question, and then look at how prepared you are to answer the question, and then look at how many points the question is worth in order to determine, should I start with this question? But if all questions have equal weight, then it's easy. You just kind of take a quick glance of 5 or 6 questions. You go like, well, this one looks the easiest. I'm going to start with that one. You guys know all those tricks, right? To answer questions, do not just go from question 1 and until you get one question entirely done, do not move on to the second question. That would not be a good strategy. A good strategy is to time yourself. If all the questions have equal weight, let's say we have 60 minutes, okay? So we have 60 minutes, and let's say we have 6 questions. So on the average, you should be spending 10 minutes on each question. So you time yourself. And then, but before you do that, you take a quick scan of all the questions, and you just mark the ones that you go like, these are insanely difficult. I'll wait until the end to answer those questions. And then you start with the easy ones. Okay? So hopefully some of the easy ones will only take you about 6-7 minutes, so you have time left. So the more difficult questions would actually have more time to answer. But this way, if you do run out of time, at least you got all the easy ones covered, right? And then you only have some of the more difficult ones that are either partially answered or not have time to answer at all, but you have all the easier one already answered. As opposed to you just get fixated on one particular question, and it's taking you like 20 minutes to answer that question. Now you don't have as much time to answer the other questions. So even though all the questions have equal weight, by sticking with one particular question, you lose the opportunity to answer some of the other easier questions that you might be able to answer like, oh, this one is going to take me like 3 minutes, no problem. So always, kind of look at the time yourself, and be ready to move on to another question if one is taking too much time. Is that okay? Of course, that is just my recommendation. It is entirely your choice to decide how you want to do it. All right, so moving on. Now we actually get to the questions, and this is zooming in a little bit too much. Got to zoom out a little bit here. All right, so this is the first question. What do you think this question is really doing? I mean, it doesn't always have a particular meaningful code. It's just that you should be able to track it down and see what it does. So in this case, do you think the loop is going to terminate? In other words, do you think it's going to get out at some point? Because it says while x mod 5 does not equal to 0, do the following. In other words, as long as x is not a multiple of 5, we are kind of stuck in the loop. So now the question is each iteration of the loop going to do something to x so that x eventually is going to be a multiple of 5? Maybe, maybe not, okay? It's a little bit tricky because this one says, we only have, the conditional statement of x gets x plus 1 is active only if x is already greater than 3, okay? But the x gets x plus 1 on line 6 is unconditional. That one is always going to run. So if you just run through this in your head, you can see how x is going to increment to 2 and then to 3, okay? And then when it gets to 4, then the x gets, if x is greater than 3 is going to be true, then you have another x plus 1 over there. So x becomes 5, x becomes 6, and then it would leapfrog now, because each iteration will increment it twice. So it would get to 10, and then 10 mod 5 is 0, because mod is the remainder of a division, so it would exit at that time. All right, well, I just talked about the whole thing. Let's go ahead and track it down. Let's trace it. So the question is to ask you to trace it. So you kind of have to trace it using the space that is allowed, that is kind of lined already. So let's go ahead and do this one. I'm just going to borrow a sheet that is already open. So we'll go ahead and give it this one a try. Line number, we have comments, we have one single variable, which is x, and that should be all. The precondition is we don't need to know anything about x because x gets initialized on the first line. So here's line 1, x gets 1. Here's line 2, x mod 5 does not equal to 0 is true because 1 mod 5 is 1. Okay, do we have any questions about that, what I just said? X mod 5 is 1. 1 divided by 5 has a remainder of 1. Is that okay? Okay, all right. So that means we go to line 3. Line 3 is asking x is greater than 3. That is false. So we don't have anything to do in the conditional statement. We skip to line 6. Line 6 adds 1 to x. X goes from 1 to 2. Then we go back to line 2. X mod 5 is not 0 is still true because 2 mod 5 is 2. So now we go back to line 3. The condition of x is greater than 3 is still false. We go to line 6. And x now has a value of 3 because of the increment on line 6. We go back to line 2. X mod 5 is not 0 is true because 3 mod 5 is 3. This time we go to line 3. X is 3 right now. So x is greater than 3 is still false. Then we go to line 4. Oops. We go to line 6, sorry. We go to line 6. Line 6 is going to add 1 to x. X is now 4. We go back to line 2. X mod 5 is different from 0 is true because 4 mod 5 is 4. Go to line 3. X is greater than 3 is now true. So you have to be very careful because now from here on x is greater than 3. So we go to line 4 and x gets incremented to 5. Then we get out of the conditional statement to line 6. X is incremented again. We just missed one chance of exiting the outer loop, but that's okay. We'll get it done eventually. Then we go back to line 2. X mod 5 is different from 0 is true because 6 mod 5 is 1. 6 divided by 5 has a remainder of 1. We go to line 3. X is greater than 3 is true. Okay. There we go. And then we go to line 4. X is now incremented from 6 to 7. Go to line 6. X is incremented again to 8. Go back to line 2. So we're going to repeat this 2 more times. No, just one more time. Yep. So on line 3, x is greater than 3 is true. On line 4, it increments to 9. On line 6, it increments to 10. Back to line 2. X mod 5 is different from 0 is now false because 10 mod 5 is 0. The remainder of 10 divided by 5 is 0. So now we get out of the loop. There's nothing after that, so we can post, and that concludes the trace. So is that okay? So it takes up about 26 lines, in this particular trace. Is that okay? Yep.
When we trace, do we have to use the greater and less than, or can we just do does not equal with the slash?
You can just do not equal to. I can't write the not equal to using a regular keyboard. That's why. Yep. Okay. Let's move on to the next question. So the next question is, this one is a pre and post condition. We are not going to have pre and post condition. So we'll skip this one. Won't talk about it. Okay, so this one is kind of like a reverse thing. Specify 4 initial values of x so that z ends up with the values of 1, 2, 3, and 4. If a case is not possible, you want to explain to me why. Okay. So now the questions are, in order for z to end up with the value of 1, after this code, x can be whatever value, or it is impossible, and then you have to explain to me why it is not possible. All right, so instead of showing you that chunk of code, let's go back to the code in question, and then I'll just kind of point to each branch, and then you tell me how we can get to a particular branch. Okay, so how do we get to this branch here on line 3? Both of the conditions need to be true, because we need to take the true branch, the then branch of the outer conditional statement, and then the then branch of the inner conditional statement, which means both conditions need to be true. If both conditions need to be true, so that means x mod 2 has to equal to 0, which means x has to be a multiple of 2. X mod 3 also has to be true, which means multiple of 3 as well on line 2. So which number is a multiple of 2 and multiple of 3 at the same time?
6.
I'm kind of surprised nobody said 0. 0 would work too, but 6 will work. I mean, 6 is fine. Okay, there's nothing wrong with 6, except it's not the first number that is a multiple of 2 and 3 at the same time. Okay, but that will work. Okay, what about the other one? Okay, what would lead me to this line here? X is a multiple of 2, but it cannot be a multiple of 3. So what is a number that is a multiple of 2, but not a multiple of 3? 2 itself, okay? 2 itself would work, 4 would work, okay? 8 would work, a whole bunch of numbers would work. All right. What about here? What does it mean if I get here? If I get here, it means a number is, not divisible by 2, right? To get here. And at the same time, it is divisible by 4. Not possible. Okay, very good. So this case is not possible, so you will have to explain to me why it is not possible, starting with the outer conditional statement. The condition of the outer conditional statement has to be false, because I'm in the else branch of the outer conditional statement, which means x cannot be a multiple of 2. Okay? But when we get to the inner conditional statement on line 8, that condition has to be true. In order for that condition on line 8 to be true, x has to be a multiple of 4. So now we are asking a question of what is a number that is not a multiple of 2, but it is a multiple of 4. The answer is you cannot find a number like that. And that's all, okay? But you do have to explain that, okay? So that is not possible. What about the last one? Is this one possible? In other words, can I find a number that is not a multiple of 2 and it is also not a multiple of 4? There are plenty of numbers, right? 1 will work, because 1 is not a multiple of 2, which forces us to the else branch of the outer conditional statement, but 1 is also not a multiple of 4, which will also get us to the else branch of the inner conditional statement starting on line 8. So 1 will work in that case. So that is how we answer this question, okay? If it works, give me an example of what kind of value of x will make it work. If it doesn't work, tell me why it is not going to work, why it is not possible. Is that okay? Okay, all right. So moving on. Question number 4 is a trace again. So this one has a few iterations. It has 7 iterations. But each iteration doesn't do a whole lot. It's more like just doing the math of it. Okay, so let's go ahead and kind of get through this one real fast, so we can use another spreadsheet or another sheet to do this. Do we have any questions up to this point about these questions? Nope. Okay. So there will be some writing. That will take some time, but otherwise it's not going to be too bad. Okay, so we have precondition. X and y do not need to start with any particular value, because the first thing we do to both variables is to overwrite them. So whatever value they start off with is going to be overwritten anyway. So on line 1, x gets initialized to 0. On line 2, y gets initialized to 0. And then on line 3, we evaluate the condition. X is less than 7, is false. It's true, sorry. It's true because x is 0. Then we go to line 4. So line 4 just has to do the calculation, but since you are not allowed to carry since you cannot use a computer, I'm going to do the hand calculation just to be fair. So in this case, x is 0, y is 0. So x is 0, 2 times y is 0, and then plus 1, so x becomes 1. Okay. And then on line 5, y just increments by itself. It becomes 1. Then we go back to line 3. X is less than 7 is true. And then we go to line 4. So on line 4 this time, x is 1 already. And then 2 times y is 2 because y is 1. So we have 1 plus 2 plus 1, which is 4. Okay. So x is now updated to a value of 4. And then we go to line 5 again. Y is incremented to 2. And then we go back to line 3. X is less than 7 is true. And then we go to line 4. And now we have x is 4, y is 2. 4 times 2 times 2 is 8. 8 plus 1 is 9. Okay. But we do not exit the loop now. It is not time yet. Okay. If we're not evaluating the condition on line 3, we do not exit the loop. So now we have to go to 5. Line 5 is just adding 1 to y. Y is now going from 2 to 3. And then we go back to line 3. Now we say x is less than 7 is false. Then we get out of the loop and get to the post condition. And what do you think is going to be the next one if we don't exit the loop? You know, from x being 9, what do you think is going to be the next one?
14 and 4.
So, well, let's just figure it out, okay? So it's going to be 9 plus 2 times 3 plus 1. 16. Do you notice something about those numbers? They're squares. Yep. So it's going to be 16, 25, 36, 47, and so on. But you don't see any squaring, you know, anywhere within the code. So it's kind of a neat trick to do it, okay? All right, so that's the answer of question number 4. And I think that may be the only one. That's the last one, right? Okay, so we're all done. So do you guys have any questions about the test, about exam 1? Exam 1 makes up 20% of your grade, so that's a pretty good chunk. But also not enough to sink you entirely if you do if you do not do very well. Yep.
So how representative is that going to be of the next exam itself? Pretty representative, you'd say?
I can't really tell because I haven't really made up the question yet. And then the second thing is, you know, my evaluation of my own test, you know, tend not to be very accurate. A lot of times people will ask me, is the test going to be difficult? I go, nah, it's going to be an easy one. And then the whole class goes like that. You know, so I've learned not to say, you know, anything about my test. So all I can say is the factual stuff. This is actually the actual test from 2 years and a half ago. And 2, I'm kind of lazy, so I don't want to come up with entirely new questions every single year. So something is going to be derived from these questions. But yet, it's not going to be the same. But I cannot tell you exactly right now how it is going to be different, because I have not thought of it yet. Yep.
Exam 1 material is going to cover which lectures?
Exam 1 material will be up to top-down design, but excluding pre and post conditions.
So including top-down, but excluding pre and post?
Yes. So you carve out that little chunk of pre and post conditions. That would be the scope of exam 1. Is that okay? All right. So let's get back to, oh, that clock is already adjusted. Nope. Nope, no. No, we're supposed to fall behind, right, by 1 hour. But not yet. Yeah, it's supposed to happen on Sunday. Yep.
I wish it was happening today. Got sparked.
Hmm?
I wish it was happening today.
I wish it happens every night. Nope, it's going to be on Sunday. So on Sunday at 2 a.m., then you're supposed to dial your clock. Because it's falling behind, so you dial it back. Ooh, that is bad.
Worst time of the year.
It's bad because my cats are already waking me up to feed them at about 4:30 a.m. That's going to be 3:30 a.m. But the good thing is I probably will go back to bed and sleep because there's a good chunk of time, before I actually have to wake up. So that's probably good. One of my cats knows how to open the door knob like this. If it's just round, it won't be able to get it. But it knows how to kind of hang its paw on this and kind of like shake it until it's down, and then it will push it. Yeah, he's a big boy. He's like 15 pounds, so, and long too, really long. A 15-pound cat, yeah. It's not fat either. He's for the most part just a big boy. All right, so we are done with top-down design. We talked about the exam on Wednesday. We talked about it being a open book, open notes exam. So I would just start preparing the material. Okay, you can print out all the modules. Okay, nothing is off limit in terms of what you can print and what you can bring to class. I think I mentioned Holy Scriptures and stuff like that too. Yes, so you can bring those too. Just in case you run out of space, you can turn in one of those pages with all your answers on them. Although some people may feel very hesitant to tear a page out of a holy book, so I don't know. That may present a dilemma on its own. All right, introduction to arrays. So we are pretty much done with the introduction. Oh, right. I think there's a new assignment too. That's right. Okay. So we have a new homework assignment. I almost forgot. So the new homework assignment is about finding the longest run in an array. So now the first question is, what do you mean by longest run? Okay, so we'll first describe what a run is. So a run in an array in this assignment, okay, because in different contexts, a run can be slightly different, but in this particular homework assignment, a run is a sequence of elements in an array that have the same value. So in the following example, okay, so this example has element 0 having a value of 3, element 1 has a value of 4, 3, 3, and then 2 of 3, okay? So in this case, the longest run has a length of 2, okay? It has to do with a bracket 2 has a value of 3, a bracket 3 also has a value of 3. So this particular run has a length of 2, and it's the longest. Because if you think about it, okay, let's say this is a run, but the next number is different. So that means this run only has a length of 1. Then we look at this one here and go like, okay, maybe this is a start of a run. Yes, it is. But it is also the end of the run because the next number has a different value. Then you look at this one here and go like, okay, maybe this guy is the beginning of a run. Yes, it is. Oh, in fact, the next number also is the same, so this run has a length of 2 now. But then you look at the next one and go like, oops, it's not the same anymore. So that means the previous run only has a length of 2 in this case. But 2 is already longer than any previous run, so you have to somehow use the logic to go like, oh, this run is longer than all the previous runs already. Let me remember the length of this run, because you just need to report back what is the length of the longest run. Then you look at this run here and go like, okay, this is the beginning of a run, but then it is only a run of 1, and that is not longer than the length of 2, so there's nothing to update this time. And then you look at the last one, okay, you can actually exit fairly early because you know that this run cannot be the longest one, because based on the length of the array and also the longest run of the known what is the length of the longest run up to this point, you know this cannot be the longest run anyway. So, but you don't have to exit like really smart and early. You just have to look at this and go like, okay, this is a 3, but then there's nothing after that, which means this run only has a length of 1, and the longest run already has a length of 2, so there's nothing to update. Is that okay? Yep.
A4, B3.
Hmm?
A4, B3.
A4 is a 3. Okay.
Okay.
So if this is a 3, then you end up with a run of 1, 2, 3, 4. So you have a length of 4 with your maximum run. Yep.
Thank you.
So the last one is kind of tricky because the last one, has you have to detect that this is the last element already, and it's terminating a run already like that. So that's kind of special consideration. Okay. So are there any questions about what you're supposed to find? Yep.
What are you presuming that you know before you start the program? Like,
Okay.
you know, like, what kind of array, the size of the array, basically?
So in your code, okay, when you're tracing it, you can assume A has 6 elements, okay, but that's only for tracing purposes because the pseudocode should not need to know the exact length of the array. You just have to refer to bar A bar to refer to the number of elements in A. But when you're tracing it, then you actually need to know, in that particular instance, how long is the array itself. Okay. So there are 2 things you have to do. The first one is to write the pseudocode, and then you have to trace your own pseudocode to kind of show that it works correctly. Okay. So in the separate tab, you called trace your own algorithm using the standard we have been using in this class. And then in your trace, array A can have the same initial value as the one that I have presented in the assignment. In other words, the first thing you want to do is to make sure that your algorithm reports the longest run in this particular case is 2. So you can check it at least. All right. So
2, or we can change it, for example, to 3.
hmm?
It should be 2.
You mean A bracket 4? You mean this one?
No, I mean the longest run. Just should be 2, or you can change it to 3. Or
Change what to 2 from 2 to 3?
longer run.
The longest run? It's entirely up to what the array is. I mean, if you have an array with the values 1, 2, 3, 4, 5, 6, then the longest run is just 1. They are all chopped up into small runs. Is that okay? Now, on the other hand, if your entire array is 1, 1, 1, 1, 1, 1 with 6 elements, then your longest run has a length of 6. Yep.
So they have to be consecutive, right?
Correct. So you're basically counting how many consecutive elements in an array have the same value,
Okay.
but what is the longest run?
Yeah.
Because you can have 3, 3, and then a 4, and then 3, 3, 3 again. So in that case, it'll be a length of 3 being the length of the longest run. Okay.
Same value and next one.
Correct. Consecutive elements having the same value. Okay. Yep.
So when we trace this, are we using the array that you have as the precondition, or do we set our
It's up to you. So the one that you turn in can be anything you want, because that's just a chance for you to test your own algorithm to make sure that it is correct. But using this one, it's what the answer is supposed to be, so you can use it first, okay? And then you can use anything other than that. All right. So are there any questions about this homework assignment? So what you need to do is to do it by hand first, okay? So always do it by hand, and then figure out, how do we do this, by hand? And try to use an example that you cannot eyeball, because if you give yourself a simple example like this that you can eyeball, it makes it very difficult to actually come up with a general method to do it. So you kind of have to think about an example that's a little bit longer, a little bit more complex, so that it forces you to use a systematic way to do it. Is that okay? Any questions? Yep.
Do we have to tell you the length?
Yes. So the only objective of your code is the length.
We don't have to tell you which element in the array is the longest?
You do not have to tell me which element. So let me find out here. It is described here, so let me just find. Okay, so when the algorithm ends, variable n, so you have to use n as the specific variable that will reflect the length of the longest run, and that's it. So that's the requirement. The requirement is you have to look into array A, and the length of the longest run has to be in variable n. But you can add additional variables if you need to. Okay, if you say, I need 3 more variables to get this done, okay, fine, use 3 more variables. So there's no limit of how many more variables you can introduce into the algorithm. But the minimum is n. You have to use variable n to report back the length of the longest run. Is that okay? Now you can use a double loop too, okay? You can use conditional statements, you can use loops, you can use pre-checking, post-checking loops. So all the concepts that we have already discussed in this class can be used in this program. And one hint is you probably need to have some kind of nested control structure, okay? It can be a loop in a loop, can also be a conditional statement in a loop, okay? And I would say the clumsy way that will still work is a loop in a loop, but a more optimized way, that is kind of more efficient is a conditional statement in a loop. But either way, you cannot avoid nested control structure. Is that okay? All right. Okay, so assuming this is fine, we can continue with our additional material. I'm thinking about, okay, this is due on Monday, which means you have a whole weekend to work on it. What do you think? Do you guys think you might need more time, or do you think this is okay? Well, I mean, doing this homework assignment is in a way studying. This has array which is not in the exam, but you still have to get familiarized with what a loop is, what a conditional statement is. So in a way, it's really helping you study too. I can postpone it to Wednesday, on the same day as the exam. Yeah, let's do that. I'm not in a big hurry I'm not eager to grade, and you have to understand grading is work for me too. Okay, so let's change it to the 7th, which is now the same day as the exam. There we go. Not a problem. Cool. All right, well, it's almost 7 o'clock. Let's go take a 5-minute break. And I'm going to walk very fast to the PE side and get some caffeine. You guys can all walk with me.
When you reach your destination, you will be faster and come back faster than you arrived.
Okay, so 7:04. Okay, caffeine. checking the, uh-oh. All right, so streamer is still streaming, so that's good. Back to the past material. Well, thank you for being here on a Friday night. I know it's Friday. All right, so the next few topics are, we are still talking about arrays. Hopefully we'll get to searching in a sorted array, but we'll first make sure that we have already finished the slide that talks about arrays in general. Okay. So we have the code to search for an element in an array, and the finalized version looks like this. Okay. So when you look at this, you go like, look at that conjunction here. So this is the one that I'm talking about. This is a conjunction. And it makes you wonder, can we switch the order between the right-hand side and the left-hand side? What do you think? As an operator, conjunction should be commutative, because true and false is false, false and true is false. False and false is false, and then true and true is true. So if you switch the two sides, it should give you the same result. But there's a little problem here. If you switch the two sides, then it is possible that the I plus 1 here, I gets I plus 1, is going to make I equal to bar A bar. So think about that scenario when I does equal to bar A bar. If you switch between these two sides, then it would try to evaluate this first. And then you will be indexing out of range because I is bar A bar already, and A bracket bar A bar is out of range because the last element has an index of bar A bar minus 1 in this case, because we start counting from 0. So now we have a problem. But if you evaluate this way, then you have a way to get out of the problem. Because if you evaluate the way that it is described at this point, which is from left to right, then when I equals to bar A bar, I is less than bar A bar is false. If one side of conjunction is false, it means the entire conjunction is false, which means you don't have to evaluate the right-hand side. So that is how we can get away with being able to do something like this, is because of, this is what we call short-circuited evaluation. There's a different name. It's also called lazy evaluation, which basically means when you're evaluating conjunctions and disjunctions, you always evaluate from left to right. And you only evaluate to the point where you can make a conclusion of what the value is. Is that okay? Okay, let me see if that word is actually introduced here. So it's short-circuited evaluation. It's not mentioned here. So, but that is that's the idea. Let me see if there's an explanation here. Nope, it wasn't explained here. So it is just kind of important to understand that this conjunction, you cannot switch the order. If you switch the order, it can potentially lead to an index out of bound problem. Because I'll explain one more time, because when I becomes bar A bar, and you evaluate this first, that will be accessing an array out of bound. And that's why you always have to check the range of an index first on the left-hand side of a conjunction. Then if everything is good, then you attempt to use the index on the right-hand side, index into it, and do whatever else you need to do. Is that okay? All right. All right, so this code can find, and it can see if a particular value is in an array or not, okay? And the array doesn't have to be sorted. So all the values can be all over the place, and it will still work. But it has a problem. It doesn't scale very well, okay? So if you think about this algorithm, and you say, well, if we have 30,000 people, what is the average number of iterations that we have to go through to find something. Well, maybe half of that, maybe 15,000 of iterations. So it kind of scales out, not very well because the longer the array, the longer the search, which is kind of what you expected. So what we'll do next is to introduce a different search algorithm that specializes in searching in a sorted array. So we'll take a look at this new slide now, which is titled Searching in a Sorted Array. Okay. Now with sorted arrays, there are a few ways to speed it up. The first way to speed it up is because the array is already sorted. If the element you're looking at is greater than the value that you're looking for, then you can stop right away. Okay, so let me clarify what I mean by that. And the best way to do it is to use a tablet. So let me start up the tablet now. And here's our notes. Okay. All right. So we'll go ahead and use an example. So let's say our array, these are the values in the array. I'm not listing the indexes. So let's say the values of an array is 3, 2, 3, 5, 10, 11, 12, and 16. Okay? And I'm looking for the value, let's say 8. Okay? Okay, now you can eyeball and find out that 8 is not here. But remember, excuse me, your algorithm cannot eyeball. Your algorithm can only look at one or two elements at the same time, and that's about it. So what you need to do now is to look at the elements one by one. You say, does 2 equal to 8? Nope. Does 3 equal to 8? Nope. Does 5 equal to 8? Nope. And then you look at 10 and go like, okay, we can now conclude 8 is not in the array. How can I conclude so fast without searching through the entire array? Because 10 is greater than 8, so are all the elements after 10, because this array is sorted. So if you're already told an array is sorted, in this case in a non-decreasing order, and the value that you're looking for is less than the element that you're looking at, then the rest of the elements to the right cannot be the value that you're looking for, because all the elements that are following 10 are guaranteed to be at least 10. So none of them can be 8. Is that making any sense? So we can optimize the algorithm a little bit to kind of make sense, to utilize this particular fact. So that means when you look at the linear search method, then the exit condition is modified just a little bit, or the stay in loop condition is modified a little bit here. I think I'm missing a close parenthesis here. Do you guys want me to fix it, or do you think it's okay? It's okay. Okay. So, because I can fix it right away, but it will just take another like 45 seconds or so. Okay, so the stay in loop condition is I has to be less than bar a bar, which means we have not seen everything in the array for sure. Okay, but the second condition to stay in the loop is a bracket I does not equal to v, which means we haven't seen it yet. Okay, well, but this is the old code. This is the algorithm that works for both sorted and unsorted arrays. Because if an array is not sorted, you cannot get out just because the value that you're looking for is less than what you're looking at already, because it's not sorted. There's no way to predict whether the next value is going to be bigger or smaller. Okay, so now we want to contrast this with the modified version, which is this one. So if you compare these two, okay, you will find that this is the only difference. We just changed the operator, the comparison operator, from not equal to just less than. That's the only change. Okay, nothing else has changed. But why does it make sense? So from here, you have to kind of think about, well, what does it mean when I get out of the loop? If you do get out of the loop, that means this condition is false, right? This is a while loop. The condition specifies when you stay in the loop. So in order to get out of the loop, this condition has to be false. This is not just any condition, this is a conjunction, which means at least one side has to be false in order for the entire thing to be false. So now you think about, okay, so let's look at the left-hand side because we always evaluate the left-hand side first. What does it mean when the left-hand side, what is highlighted right now, is false? Well, if this is false, it's saying I is less than bar A bar is true. Excuse me, I is less than bar A bar is false, which also means I is greater than or equal to bar A bar. But that means, the index is now out of range. Well, the only way for the index to be out of range is for me to have examined the entire array already. So to get to this point means the entire array was already examined and none of the elements has the same value as V. Well, that seems to be a pretty good reason to get out because, what we are looking for is not in the array at all. Let's look at the second condition. So assuming I is less than bar A bar is still true, which means I is a valid index. The second condition is A bracket I is less than V. As long as A bracket I, which is the element that we are looking at, is still less than the value that we are searching for, yeah, let's stay in the loop and maybe the next one is going to be the value that we're looking for. Why? Because the next one is going to be greater than or equal to A bracket I, which still has a chance to be equal to V. Is that okay? What does it mean when the highlighted part is false? In other words, what does it mean when A bracket I is greater than or equal to V? Well, they are actually two separate cases. Greater than is one case, equal to is another case. Let's deal with the easy one first, equal to. What does it mean when A bracket I equals to V? Eureka, we have found it, right? The algorithm only has to find one instance. It doesn't have to count how many. So as soon as you find one and say, oh, the value V is actually in the array, then it's time to go, okay? It's time to exit the loop and let people know that you have just found the value V in the array. So that's equal to. What if A bracket I is greater than V? Well, that means A bracket I plus 1 is also going to be greater than V. A bracket I plus 2 is also going to be greater than V because array A is known to be sorted. So that means none of the other elements of A can match the value of V, so now that is also a reason to get out. Is that okay? So after you get out of the loop, then you have to look at this condition to evaluate what is the conclusion. If I equals to bar A bar, that means you have exhausted the entire array. None of the element matches the value V, so that means no element in A has a value of V. What if I is less than bar A bar? Then you actually have to compare A bracket I with V, because in that case you have two reasons to get out of the loop. Whether you have found it or you have confirmed that nothing after A bracket I can match the value of V. So now you do have to compare to confirm that there are no elements in A having the value of V. If this condition is false, that means you have just found the value of V in the array. So are we doing okay so far with this? So this is slightly better, okay? Because in the original code, if a value is not in the array, you have to go through the entire array to confirm that. This one, well, you can get out a little bit earlier. But it is still called linear search, which means the amount of time that it takes to search for something in this array is quote unquote linear to the size of the array. Okay? What that means is on the average, if it takes you X amount of time to search in an array that has n elements, if you double the size of the element, it will double the amount of time. If you quadruple the size of the array, it will quadruple the amount of time. That's a linear relationship. Is that okay? All right. So the next thing we want to do is to say, well, are there any way that's faster than this? Well, as it turns out, there's a method called binary search that is actually a lot faster. I think we have enough time to talk about this entire search algorithm tonight. So the first thing I want to do is to really just kind of show you how fast we are talking about or how efficient we are talking about. What is world population at this point? 7 million something? We'll call it 8, okay? We'll call it 8 billion people, okay? So now the question is, if there's a unique ID for each person, on the entire planet, okay? And you have a database, you have an array of all of those unique IDs. If someone gives me a particular ID and say, well, is this person on Earth, okay? Or is this a valid ID of someone on Earth? How many times do you think I have to compare to confirm that? Either, yes, that person is here, or no, we don't have anyone with that ID. How many comparisons do you think we need out of 8 billion records?
Potentially 8 billion.
Okay, potentially 8 billion, that's one guess. Any other guesses?
How many times can you cut it in half before you?
Aha, okay. So that's kind of that's the right answer, but a little lazy. I'm just kidding. It's the right answer. It's how many times we can cut it in half, okay? Because that's the idea of binary search, okay? So what you need to do is to kind of imagine, we have a huge stack of cards, okay? 8 billion cards, okay? So it's going to be pretty big, but it's sorted, okay? So I'm assuming the ID is sortable so that we can actually sort all the cards with all the IDs. So the trick is, if you're given a new ID and you go like, okay, is this ID in this particular stack? So what you do is you don't look at the beginning, you don't look at the bottom, you go straight into the middle of the entire stack, you pull that one out and go compare, okay? Now, very, very occasionally, you just have a match right there, okay? But most likely, it's not going to be a match. But what if it's not a match? Well, if it's not a match, and the number, the ID that you're given with, if it is less than the ID that you have pulled out of the stack, that means the bottom half of the stack cannot have that ID. So you now eliminate that one half, and you got 4 billion records left. Okay? What do you do with those 4 billion records? Cut in half, take a look at the middle. If the ID that you're given with is greater than the card that you just pulled, then you discard the first half. So now you have 2 billion of records left. You do exactly the same thing. 2 billion becomes 1 billion. 1 billion becomes 500 million. 500 million becomes 250 million, and so on. So every single comparison cuts the stack, the size of the stack, in half. So now the question is, how many times do you have to cut in order to get to one single card? So that one single comparison will confirm whether the ID is valid or not. So you can do it on the calculator, okay? Many of you know how to do log already. You can also just keep dividing by 2 until you get to something that is less than 1, okay? Which is kind of repetitive and kind of boring. Or you can do it with mental math, okay? So I don't know the exact answer right away, but I can do the mental math. So the mental math, trust me, this is not mental math in like those crazy math competitions where people have to do squares and square roots and exponents and log in using the biological brain. This is like super duper easy. Okay. And I'll show you, this is a very useful trick in computer science also. Okay. So in computer science, we look at 1024, which turns out to be 2 to the power of 10. This is the exact value of 2 to the power of 10, which is 1024. Go like, that's about the same as 1000, which is exactly 10 to the power of 3. So this turns out to be a very, very useful estimate. Because once you have this estimate, then you look at 8 billion. 8 billion. Right? Okay. So this is a 10 to the power 3. This is another 10 to the power 3. This is another 10 to the power 3. Then you go like, oh, this is approximately 2 to the power of 10, 2 to the power of 10, 2 to the power of 10. Are we doing okay so far? Okay, this is rough, okay, it's not exact. And then you have an 8 remaining here, but the 8 is actually just 2 to the power of 3. So now you add up all the powers. So you basically say 8 billion is about approximately 2 to the power of 33. So that means you cut 33 times. In 33 comparisons out of 8,000, 8 billion records, you can confirm whether something is in it or not. I think that's pretty fast. The best part is, what if we found some source of energy or some GMO crop, and now we can support a world population of 16 billion. And we want to find one record out of 16 billion. What do we need to do? How many times do we have to search? 34 times. Just add one. Isn't that a good deal? Let's say mankind expands to the rest of the solar system, and the population doubles again. Now it's 32 billion. Now it takes 35 comparisons. Yep. And then we start to send off ships to colonize other solar systems. World population doubles now to 64 billion. Add one more comparison. I think that is pretty cool. Okay? So that is the whole idea of binary search. And when we look at binary search, this is the deal. Okay? The execution time is the log, is relative to the log of the size of the array. So when an array doubles in size, you add one comparison. Is that okay? All right, so it's easy to talk about the numbers, it's kind of abstract, and it's also kind of easy to talk about, oh, this is really cool, but does it really help you when you become a developer, when you become a software engineer, when you get a job? Is this stuff going to be helpful? What do you think? Yes. Probably, but in what way is it going to be helpful? Because your boss is not going to ask you, hey, Tack, do you know the time complexity of binary search? Well, actually, my boss may, if my boss is a boss in Google, probably this is like an easy peasy answer to the boss, okay? So, but yes. But why do you think understanding this sort of thing is going to be helpful in your career? I'll give you a scenario, okay? Now, some of you know that the Bay Area is now approaching the same condition as in year 2000. We kind of know, well, the older folks know what happened in 2000. Nothing. What happened in 2000 around the Bay Area? If you have a picture of streets of San Francisco in 1999, okay, and you compare a picture of the same place in, let's say, 2005, okay, what do you think you will see as change? There's nothing, okay. Basically, all the high-tech companies, they lost their venture capitalist funding, and they all folded. So it becomes a cascading problem, because when the venture capitalists pull their funding, all of these startup companies start to collapse. When the startup companies start to collapse, then all the employees of these startup companies become available. So now the stable employers like Google and the bigger employers like HP or Oracle will now say, hey, we don't need to we don't need to tolerate these crappy and inefficient programmers anymore. You are fired. So a bunch of people got fired because now these stable employers can hire all the top-notch people who used to work for the venture capitalist companies. Is that okay? So a whole bunch of people lose their income. They cannot afford those houses anymore because the housing market was like this around year 2000. So the housing market itself collapsed. The housing market collapsed, so investment collapsed, and everything just went down the toilet, including the stock value of even big companies like Intel. I know a neighbor who used to work for Intel, and he thought, well, after working like 30 or something years at Intel, I have this much stock, as investment, for my retirement. It's time to retire, and then this happens, and then the poor guy has to go back and work another 10 years. Cannot retire, cannot afford to retire because the stock value of Intel just like that. Okay. So anyway, So let's say the same thing is going to happen again. It will happen again, we just don't know exactly when. Okay? And your company is downsizing, and it's down to me and Pat in the company. How do you think the boss is going to decide who gets to stay? Well, who can write better code, right? So the boss says, whoever can write better code gets to stay, which makes sense, okay? So the boss decides to arrange, let's say, a coding competition, okay, and say, whoever can write the program that executes the fastest is going to win and be able to stay in the company. Is that okay? So let's go to a spreadsheet to look at these numbers, because until we actually look at the numbers, sometimes we understand, oh, this is log and this is exponent, but we don't really appreciate what those numbers are representing. Okay? So we'll go ahead and look at the problem size. Okay, problem size, which is basically the size of an array. Okay, size of array. And then we'll look at how much time text computer is going to take to solve the problem. So we'll start with a problem size of 1, okay, which means we're talking about an array of 1 element. You go like, who would want to use an array of only 1 element? Doesn't that defeat the whole purpose of having an array to begin with? Well, just hypothetically, we can have it, okay? So with only 1 element, how many comparisons do you need to confirm whether an element is, a value is in it or not? 1 comparison, okay. Does it depend on whether it's linear search or binary search? Nah, it's the same. Okay, so text computer we'll be measuring in nanoseconds, okay? And because Tech is an old timer in this company and never asked for an upgrade of his computer, I'm still running a 486 computer. So it's extremely slow, okay? So my computer takes a long time to do this computation. So just for argument's sake, my computer takes 100,000? Yeah, 100,000 units of time, okay? And then Pat, being a super duper, superstar, employee who was just hired like 3 months ago, get to use the latest and greatest i9, top of the line liquid cooled computer, which can get the same thing done in 1 single comparison, but it will only take 1 unit of time instead of 100,000 units of time. Okay, so my boss looked at this number and go like, Tech, you're going. I go like, well, wait. Let's make the problem bigger, and we'll see again, whose algorithm is faster. But instead of doubling, I'm just going to say, let's have 1 plus 1. Let's have 3 elements in the array. Okay, so with 3 elements in the array, okay, so think about 3 elements. So you got 1, 2, 3, right? In binary search, we take the one in the middle, and then we go, okay, which way should we go, right? But whichever way we go, we only have 1 left to compare. So in 2 comparisons, I can conclude whether the value is in the array or not. Is that okay? All right. So my algorithm will only take whatever it took to solve a problem of only 1 in the array, and it will double the time. Okay, it will just add 1 to that time. And Pat's computer, on the other hand, is going to take 3 units of time because it's linear search. So in the worst case, if the value is larger than everything else in the array, even using the optimized linear search algorithm, it would take 3 iterations to confirm. Is that okay? Obviously, my boss says, you're still going to leave because 200,000 is still a lot more than 3. In fact, the distance is now increasing. If you think about the distance between 100,001 versus 200,003, the gap is actually increasing. The ratio is not, but the actual absolute value of the gap is increasing. And go like, wait, let's do something else, okay? Let's double the size of the previous problem plus 1. Okay, you can see that I'm starting to use a formula to do it because there's a way to calculate it. So with 7, how much time do you think my computer would take to solve the problem? So imagine it's 7. So if I take 1 in the middle, then I only have, each stack is only 3 left, right? But only one contains the value that I need to search, right? So I discard the other one. So the problem becomes 3, which I already know will only take 200,000 units of time. So I just have to add 100,000 units of time, and that becomes it. Okay? So my computer now is this value plus 100,000 units of time, which is now 300,000 units of time. Pat's computer is just going to be same as the size of the array. So the gap is still increasing. If you look at the actual gap between 300,000 and 7, that gap is increasing. But the ratio is actually starting to decrease. So what do you think is going to be the next one? 15, So 15, like that, okay? And according to this trajectory, do you think I can catch up? In other words, do you think at some point I'm going to beat Pat? And when do you think I'm going to beat Pat? Well, it has to do with 100,000. How many division by 2, is needed? Okay. It doesn't take much. Okay, still not there. Oops. Control Z. Of course, there's a theoretical answer to it too. You can solve for the equation. Okay, so this is the crossover point right there. That's the crossover point. So when the problem size is approximately 2 million records, my computer is about the same. That's the last competition that I am losing by just a little bit, okay? And then the next one, when the problem size is 4 million, excuse me, only 4 million something, my computer is already faster. So that means if you choose an algorithm that has an inherently faster nature to it, you can use an older machine, okay? But eventually, when the problem size is big enough, your slower computer, but using a more efficient algorithm, would actually beat a faster computer running a slower algorithm. Is that making any sense? Sort of, okay? So this is really important because a lot of people don't pay attention to this sort of thinking when they're writing programs. Okay, so let's say you're looking for something that can search. Okay, there are many search algorithms online. You can just kind of plug something in. But if people are not careful, then they would choose an algorithm that does not scale up well. And what happens is when you're testing the algorithm, when you have smaller test cases, everything is fine. Okay, it's all cool. But when your problem is getting bigger and bigger, then the problem starts to show up, because then you will realize, oh, I'm writing this with a word processor. It works fine when what your document is only a few pages long. But if I try to type a dissertation or a longer paper in it, like 50 to 60 pages, suddenly things don't work anymore, because somebody chose the wrong type of algorithm to use. And you might think, well, that's just fable. You're just talking about something that cannot possibly happen. Well, I tell you, it actually happened. When I wrote my dissertation, I was writing my dissertation in Microsoft Word 2.0. I'm not kidding. It was 2.0, and halfway through my dissertation, they upgraded it from 2.0 to 6.0. I have no idea what happened in between, but Word just changed from version 2.0 to 6.0. And I have a lot of cross-indexing, okay, refer to chapter blah, blah, blah. There's a reference to an earlier chapter. There's citation at the bottom. So there I'm using Word, more advanced features of Word, okay, including some pictures, a little bit spreadsheets, but nothing too heavy duty. And then at one point of the writing of my dissertation, Word just couldn't handle it. It just crashed out. Okay, I'll be halfway typing my dissertation, and then everything stopped. The hard drive light stays on forever, and I go like, this is not good. And there was no way for me to terminate Word either. So I had to basically just reset the computer. And fortunately, the document was not entirely lost, but it loses a chunk of it. I cannot remember even how I fixed the problem. I think I had to break it down into like sub documents, and then use like all kinds of manual methods to kind of put things back together from the smaller chunks and stuff like that. And my dissertation was not long. It wasn't like a 300-page kind of thing. It was only about 50, 60, 70 pages, and it is double spaced, using 12 point font. It's not high density by any means, okay? And it couldn't handle it. It could not handle it. So I'm guessing somebody was using a wrong algorithm. It worked okay for shorter, Word documents. If you're just typing a memo or something like that, 3, 5 pages, no problem. But once it gets to only 60 pages with a lot of cross-referencing, it just died. So it does happen. Okay? So that's why this sort of thing is kind of important, because now, of course, the competition between me and Pat was a little bit exaggerated, but it does give you an idea of, choosing the right algorithm can beat, using older hardware. Is that making any sense? Okay. And then the second question is, well, is it really realistic that my computer is 100,000 times slower than Pat's computer? What kind of, time period are we talking about to have that kind of difference? What do you guys think? Let's work out that math too. I like to work out stuff, numbers. Okay. So let's work out that number. So we are talking about 100,000 times slower, okay? Does anyone know what is Moore's law? M-O-O-R-E. Yep, go ahead.
Every 2 years, transistor size halves.
Okay, so not 2 years, okay? So you're close. So every 18 months, okay? For every 18 months, the transistor size halves. Okay, so that part is correct. So transistor size halves. Okay, and that approximately equates to density, which means you can pack twice as much stuff onto the same die. And it also kind of it also equates to speed, because the smaller the things, the more you can pack into it, and the faster you can change to. So that usually translates to speed as well. Okay, so when you look at this, we will just kind of say, well, it's approximately saying, every 18 months, okay, every 18 months, processor speed doubles. Okay, there's a 2x. So the question now is, how many 18-month periods does it take to achieve a improvement of 100,000 times? In other words, how many 2x do we have in 100,000? Remember that trick that we just talked about earlier? This accounts for 10 of those, and then 100 accounts for 7 of those, because 128 is 2 to the power of 7. So we need 18 months to do it, which is 17 times 1 year and a half. So that is approximately, what, 24 years. In 24 years, the speed of a typical processor will be 100,000 faster, 100,000 times faster. And some of you do not have that sense of time scale because you're too young. But since I'm more than twice of 24 years old, I can tell you what 24 years seem like. Okay, so 24 years ago, what was I doing? I think I graduated from, okay, so today is 18, so 24 years ago is, what year was that? Was it 94? Okay, so 94, I was just about to get my dissertation, so I was just about to graduate from graduate school. Okay, so those computers were literally about 100,000 times slower than the computers today.
Pentium 1s and Pentium 2s.
Huh?
Pentiums.
They were Pentiums, yes. And I remember those were M. Oh no, that's before the M, Pentiums too. So those were much slower. If you don't believe me, you can try to find one of those older computers and run those and see if they. Yep.
I mean, maybe this is anecdotal, so just stop me if I'm going off about something we don't have time for. But when the first computer I ever got to use was running DOS and Windows 3.1, and then I didn't get to experience Windows 95 or 98 except when I went to my uncle's house, and then we got about XP pretty close to the release date. So, and I was like 7 when I was using DOS, so it's like, yeah, just even getting XP in the home was such a big deal to me.
Okay. So here we have. Yeah, go ahead.
I could tell when people played this game Shovel Knight when it came out. It wasn't on Mac yet because that's the computer I had at the time, and so I grabbed my parents' old PC, which came out literally 10 years before this game came out. And despite the game being able to run on like a 3DS and like very weak hardware, it still ran about a quarter speed.
Mm-hmm. Yep. So I found hard data here. Okay, I found hard data. The Intel Pentium processor, and this is before MMX technology. The clock speed is 75 megahertz. And that is single core. Okay, they do not have the concept of multiple core either at the time. The size of each transistor was somewhere between 0.6 and 0.35 micron. They are now down to 14 microns. No, excuse me. They're down to 14 nanometers. Okay, 1 micron is 1,000 nanometer. They're down to 7 now.
Compare the clock speed to now.
I know.
Do it. Pull up the current i9 clock speed compared to that.
i9s run at 5 gigahertz. The more consumer models run at like 4 gigahertz.
Yep. So when you combine all the things about multi-core, improved technology inside the processor itself, and then you're talking about 64-bit processors now instead of 32-bit processors. So each clock is actually doing a lot more. Each computation is doing more. So I would say the estimate of 100,000 times is actually not too far off the mark. We are talking about huge improvements here. Okay. Now I know this is an introduction to algorithm design and problem-solving class, but if you have an eye on the trajectory of technology, it's going to be very helpful, because this is not automotive technology. It's not diesel technology, where things do change over time. There's huge improvement in terms of emission control and stuff like that. But it's nothing in the same order of magnitude that we are seeing in computer science or in computer technology. Okay. So what you want to do? Okay. I know I'm digressing even more and more, but this is important stuff, because it gives you an idea of what you can expect in the next 10, 20 years. Because I'm hoping you guys are all expecting to continue to work in about 24 years, right? Okay. Well, the AI stuff, that's a big unknown.
If I were a cyborg in 24 years, I'm going to be severely disappointed.
Well, that may or may not happen. But anyway, so if you dial the clock all the way back, okay, to Alan Turing's time, okay, what time frame was that? Okay, when you watch that movie, The Imitation Game, what was the time frame? The end of World War II. So we are talking about the late 40s, okay, the late 1940s, okay, and now we are in 2018. So you look at all the technologies, okay, not just computers, but aviation. Look at airplanes. So they had jet engines at the end of World War II. And those fighters were able to do Mach, 0.6, 0.7 maybe, okay? So we'll call it 0.7 Mach, which is the speed of sound, excuse me. Speed of sound, okay, speed of sound. And the latest fighters can do what? Mach 3 maybe, Mach 2.5, Mach 3. So we are looking at an improvement of, let's say, 5-fold, okay, 0.7 to 3.5. 5-fold over 70 years or so, 70 to 80 years. Pretty impressive. I mean, if you think about it, okay, snap, okay? The moment you hear that sound, that's the speed of sound. And the airplane can go like 3 times that speed. That is pretty darn impressive, okay? But it's nothing compared to the speed of computers, okay? So if you just have to think about an alternate universe where aviation technology was way superior than what it is now, but nobody did anything to computer technology. So there was no progress of computer technology at all. Will we still have drones? Will we still have autonomous drones? Can anyone imagine how much computation hardware it will need using 1950 technology in order to automate aviation? You will have like a fleet of B-52s carrying nothing except for computational hardware, and they will have to be tethered because each B-52 can only contain one portion of the computer. So now you have big, huge cables tethering all of these B-52s flying in formation. And then on top of that, something has to generate all that power for this gigantic computer. That is the kind of thing that we'll be looking at if we have no progress whatsoever in computational technology. And it's still moving forward. Okay, computational technology is still moving forward. Why is that important to you? I mean, you're just here getting through this class so you can get onto cisp300, but why is this stuff ultimately important? What kind of jobs do you think you will have? Computers are not just getting faster, but they're also getting cheaper, right? They're getting cheaper, they're going faster, which enables emulation of just about everything. Okay, it used to be just the national labs being able to do nuclear bomb test without actually firing up nuclear bombs, but they can now do emulation with just about everything. Robotic technology would not be going anywhere without computation. Just think about Segway. Okay, that thing that only has 2 wheels, people can step on it and it stays balanced. Without technology, without computing technology, that would not have been possible at all. Okay, so a lot of old research topics that was deemed impossible, impractical, or undoable in the 80s and in the 90s is now back. Okay, neural nets. Has anyone heard of neural nets? I sure hope you guys have heard of neural nets, like deep neural nets, back propagation neural nets and stuff like that. That was kind of hot in the late 80s and early 90s, and then suddenly there was no research. Nobody put any money into it because we didn't have enough computation power to make it useful for anything. The theory was there. People knew that it was able to do certain things, but because of the lack of computation power, it just died. And now it's getting picked up again because we now have the computation power to actually make use of it. So that is the kind of thing that we are looking at when we are looking at this change of technology, the improvement of speed of computers. It makes things that were impossible to do in the past possible now. So by the time you graduate from a university, things will be different again. Okay, there will be application of technology to many other industries that do not yet exist. I'll give you a few ideas. Fake news factory. I'm not kidding. That will be an industry by the time you graduate. It will be an industry probably bigger than entertainment industry now.
Isn't that an industry already?
Hmm?
Isn't it an industry already?
Yes, but it is still not at that level. And then there will be anti-fake news industry. No, think about it, okay? If someone is generating fake news, there will be someone who needs to counter the generation of fake news. So that's going to be a big thing. We don't have those industries now, but they will be there. What else do you think will be there by the time you graduate? Yep.
Oh, no, just one.
Oh. Think about user interface. Think about user interface. We got keyboard, we got mouse, okay? We got touch screen, right? What else is coming along?
Those foldable phones.
VR, okay? VR and AR. Now VR and AR are related, but they're not exactly the same thing. Does anyone have a new cell phone that is AR Core certified or AR? The new Apples have their own name for the AR stuff. Do you have an AR Core?
But not the new thing.
The new thing? Okay. So AR Core, is augmented reality core. It is an addition or an extension of Android. So now the question is, well, what's the big deal? Well, if your phone, my phone is not AR Core certified, so it can't do it. But it makes use of a camera, a single camera. We are not talking about like an array of cameras or anything that's fancy. It's a single camera. And what you do is you just, kind of like scan over an area like this, okay, a few times, and then you stop. And by the time it stops, your cell phone would have built a 3D model of what it have just seen, okay? So now you can, quote unquote, put something on the desk in the virtual world, but when you look through your phone, look through the lens of your camera of your phone, that object will be there. And when you pan and tilt and look at it from different angles, your phone would look at that object as if the object is actually on the table at a particular spot. That technology is already here. It wouldn't be possible without a massive amount of computation power on your mobile phone, because that computation is not being sent back to the Google Cloud to do all the computation. It is actually done on the phone itself. What is that going to be helpful for? Engineering, medical science. Okay, so let's say there's a surgery somewhere in Nebraska. Okay, and they don't have a lot of top notch surgeons, right? So in the emergency, so let's say the local doctor did not know what to do about this case. Okay, so the the doctor would call nurse, AR Core mobile phone. The nurse would then use a mobile phone, scan over the operation area, and then send it to a top-notch surgeon somewhere, let's say in San Francisco, in UCSF. Okay, so that surgeon in UCSF will now interact with the operation area remotely and virtually. And then the doctor, who is actually standing in front of the patient, would have an iPad kind of put right next to him, so that the suggestion of where to cut, where to pinch, where to do whatever operation thing they do, basically projected onto the actual thing. So they would know, the doctor would now know, okay, I need to do this first, and then I need to cut this, and then do this. That technology will be here. And it will be used in more ways than I can possibly think of. And by the time you graduate, which is about 3, 4, 5 years from now, that technology will be mature already at that time. Now, if you combine augmented reality, which is kind of cumbersome because now you have to hold your phone like this, combine that with VR, virtual reality. So now the doctor doesn't need someone to be holding an iPad in front. So now the doctor can actually look at the operation area and actually see all the prompts, the interactive suggestion from the top-notch doctor in UCSF, even though the doctor is actually in Nebraska. That is coming. I think it's coming.
That's a scary tutorial. Would love for that in table.
A company that tried to redo Google Glass.
Uh-huh.
Where it was basically just that.
Yep.
And it would let them, artists could create in 3D space using just their hands and
Yep.
motions from their eyeball. And
Well,
it would use it was supposed to transmit a laser into your retina, so it was super
high resolution.
where
Mm-hmm.
It's supposed to be able to just use like movements from your eyeballs to like
Yep.
see everything.
Now, if you have an AR core capable, cell phone, one of the first few apps is the IKEA app. The IKEA app, basically say, okay, you just scan your living room, a little bit like this, okay, and now you go to the IKEA catalog and go like, I kind of like this couch, but I don't know how it's going to look like in my living room. So you take that and then you say, plop it over here, and now you can just walk around and look at your living room as if the couch is actually there. And you can say, well, next to the couch, I think I want to have a shelf, or next to the shelf, I want to have an entertainment system, and then a dining table. You just put all those furniture in your kind of your room, and then you can walk around. You just have to do this the whole time, but you get an idea of what it looks like. So if you think about virtual reality goggles, if they can get small, high resolution, and small, high resolution, and wireless. Okay. So it's just like you're putting on a regular pair of glasses.
What's with this company? I'll send you an email with
Sure.
the thing.
Yeah, but when you combine these two, it's killer, right? I mean, because now you can just kind of walk around as if the furniture is there. And you just walk around. Doing.
Clip of the dude, he was like, I want to turn my office into an aquarium. And so he like swiped with his eye and like everything in the office turned into like fish and like everything. It was really dope.
So when the boss comes in, you see a hammerhead, right?
I mean, technically, yeah.
With the sound effect of your jaws, like dun
Because
dun
that was
dun
one
dun
of the
dun
things
dun dun dun.
they wanted you to be able to create like in your own space whatever you wanted, and anyone
Yeah.
else wearing the glasses would be able to walk in and see what
Yeah.
you've done.
Yep. Yep. So I know we are running out of time, so you're, I think it is a good use of class time, because I think understanding the trajectory of technology sometimes is just as important as the details of, how to program. That's just my belief. That's all. Yep.
So I have a computer, and
Mm-hmm.
I know it works when I turn it on, and that's all I know about it. Is that going to become a problem?
No, it's not going to be a problem because somebody who knows a lot more about computers can, over the net, over the wireless, tell you everything else that you need to know.
Okay.
Yeah, that someone else may be an AI. If you guys have not watched the movie called Her, H-E-R, that's the name of the movie. That's a really, really awesome movie to watch. Okay, it's not an INTP kind of movie, because it's more of a feeling type movie. But the technology part of it is also really awesome. It's just a projection of how things may become in the near future. Yep.